There's a what?
The speed.
Speed for your, the speed matter? No, correctness matters. Yeah, if your code is running slow as hell, don't worry about it, right? To get it to actually be a computer algebra system, like would take all term, right? That's what a computer algebra course would look like, because we're all using the worst arithmetic, right? So if we really wanted to make any of this fast, we'd have to put a lot of energy into making all of the basic arithmetic fast. Now, if we got like a lot slower, when you don't think that it should, then maybe, yeah, like we can take a look at it. There should be a Julia profiler that tells you where you're spending all of your time in running. He's nodding, so maybe you could.
Oh, that's a great idea.
Yeah. Okay.
Like for CRT, for example, we're literally doing multiplication. It's normal multiplication. Like,
yeah, like the CRT really shouldn't be that, like you're not going to see CRT gains until the products that we're doing like require big integers properly.
I think, yeah, we're not actually doing big ones.
Because if you're using just regular integers, then you are working mod p to some extent, right? You're just working mod 2 to the power of 64. So as long as it's correct, like there could be some perils with Chinese remainder theorem if you're not updating one by one. If you did all the products at once and then recombined it, that's a bad idea. If you copy the pseudocode, then yeah, that should be, yeah. But maybe what you can try to do is run the code profiler. I'm sure, like someone ran this last year. I'm sure there's a tool, and it will tell you what the slow part of your code is. But I wouldn't be overly concerned about it. Okay, so what I want to do today, like that this is just sort of a revision session. So we're gonna work together to try to help sort out each other's problems. I'm certainly here to help you understand any of the math that I may have poorly explained. I have lots of scrap paper. I brought whiteboard markers and everything, but I just wanted to go over this one optimization that you had to do for power mod. So remember, we were talking a little bit about this last week when doing factoring. There was this super special polynomial that we need that's kind of like x times the cyclotonic polynomial, or a cyclotonic polynomial is something like x to the power of p to the k minus 1. And this is super important because it happens to be all the product of irreducible polynomials that divide k. What we're doing, though, is working in like a restricted sort of ring of numbers, right? Like mod 17 or mod 101. So if we're not super careful about how we compute numbers like this, we can really do something quite silly. So suppose we want to take 8 to the power of 17 cubed, mod 17. What's the largest number mod 17? 16, right? So letting this number grow to anything in excess of 16 is silly. Now, 8 to the power of 17 cubed is actually 7, followed by 10,000 digits, followed by 8. A very, very, very large number. Certainly something that is not going to be a machine computation. This is really going to push the limits of your computer to actually compute this. So we're not going to go and blow up a number that's 10,000 digits just to reduce it to mod 17. What do we want to do instead? Well, every time we multiply by 8, right? This is what a power is, right? If we want to do 8 cubed, it's just 8 times 8 times 8. Now, what I'm saying is every time we do a multiply by 8, we should also immediately reduce. So you should go 8 times 8, and then go mod 17, right? So that's 64 reduced to 17. Now that number is small and you want to multiply by 8 and immediately reduce by 17 again, right? So this is going to prevent the number from ever exploding to something huge. And this is extremely important, right? Because otherwise, I don't even think Julia would be capable of doing something like this. Now, is this the best that we can do? Suppose you want to do 8 to the power of 17 cubed, and we're going to do it naively. How many multiplications are we going to have to do? 17 cubed multiplications. Now, That's also something that we want to optimize. Consider this. Suppose I want to take some number to the power of 103. Naively, that's going to take 103 multiplications, right? But let's study this instead. How many multiplications does it take to get w squared? 1. How many multiplications does it, once we have w squared, how many multiplications does it take to get w to the power of 4? 1, because we square w squared. What about w8? You square w4, right? And so on and so forth, right? So to get w squared all the way up to w to the power of 64 requires 1, 2, 3, 4, 5. That's 6 multiplications. Okay, but we want it to be 103. Well, how do we get 103? Well, 103 happens to be 64 plus 32 plus 4 plus 2 plus 1. You can pull that out by just looking at the binary representation of 103. So that means to get something to the 103rd power, we can take that to we can compute all of these powers of 2 and then multiply w to the power of 64, 32, 4, 2, and 1. That will sum to 103. And therefore, we've done w to the power of 103, not in 103 multiplications, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 multiplications, which is way less. That's an order, that's a logarithmic relationship rather than well, something worse than logarithmic. So here is how you could sort of do this, right? If we wanted to compute 8 to the power of 17 cubed using this power mod technique, I would say, okay, 17 cubed happens to be this number, base 2. So I need to multiply 2 to the power of 12 by 2 to the power of 9 by 2 to the power of 8, 5, 4, 2, and 0. So here we do 12 multiplications to get the powers of 2 by squaring. So we start at 1, 2, 4, all the way up to 12. And then we do 5 more multiplications, right, to get the 17 cubed. So instead of doing 4,913 multiplications, we're only doing 12. So this is not overly complicated to implement. I think the hardest part here is that given your m, you have to come up with this binary expansion. And then you build up all of your powers here, and then you just include them or exclude them depending on your binary representation. Okay, so is there any questions about that PAL mod technique? Because there's two things that you have to do, right? Every multiplication should be done mod 17, and you shouldn't be doing 103 multiplications to take something to the power of 103. You should be using these squares. Yes? As long as you're, well, certainly the this part is more efficient because you're certainly reducing the number of multiplications. The other thing isn't really an efficiency thing, but it's more of a sensible data representation type of thing. It's like, I know that this answer is going to fall between 0 and 16. So why let it grow to something with 10,000 digits, right? If we can always just insist on staying between 0 and 16, right? So this is sort of more for speed. You'll certainly see a speed up here just because that number is so huge. But again, it's more of like a data representation thing. This thing takes a computation that may not be possible with the computer and turns it into something possible, because this requires a programming language that allows for arbitrarily sized integers. And furthermore, we have to assume that integer can actually fit on the memory of the machine, because the machine can say you can use the largest integers that you want, but really the biggest one you can use is anything that fills up your RAM. And this does happen, right? If you actually start doing real scientific mathematical computing, you start having objects that don't fit into memory, right? Including numbers themselves, which is a problem. Yeah.
We didn't even speed up if we did like repeated cubing in a different number-based system. Because then there's fewer multiplication.
Well, but okay, but here I'm squaring,
yeah.
Right? I'm saying w squared is w4.
So it's a single.
So would you be able to do that with cubes?
It's like 2 operations per cube.
So you get what, 1?
But the number's smaller in time. There should be fewer ultimate products to make it those things.
I'd have to work this out, but something's telling me that it's not the same. Because if you do cubes, then you need w to the 1 and w squared, right? And then you have to like sort of multiply those both by W squared to get W3 and W4.
Yeah.
Like, I'm not sure this has the same nice property,
Okay.
because when it's binary, we're saying included or excluded, and those are the only possibilities for here. If you changed it to cubes, what does having a 2 there mean?
Yeah, no, I think you're right, actually, I think cubing is.
I'm not saying it's not possible to do it that way, but I think it actually may introduce more multiplications than it would be in the binary one. But I don't know. This is something that I'd have to work out.
Yeah, fair enough.
Do it this way. It's easier this way, right? Because if you look at the code, that's all I'm doing, right? I'm multiplying my answer by the current power if it corresponds to a 1 in the binary expansion, right? That's fairly straightforward. Yeah.
Okay, like what is it?
Yes, of course. Well, I think you'd have to instruct it to do power mod though, because it needs an associated prime number. It may be doing this type of squaring naturally, if it was smart, but yeah, but now you know what it's doing, right? So somehow occasionally we have to look under the hood at how these tools are built, and then you have to build them so you can appreciate when you're just using them from the libraries, right? Because a lot of these techniques that bring us into the realm of actually being able to compute stuff like that, that's fairly clever. Like, we look at this now and say, this is so obvious, but it's like, well, someone still had to figure it out. It wasn't obvious when we first did computers, and we first had to discover that this was a problem before having a solution given for it. And so now, speaking about problems and solutions, so what we're going to do for the rest of this class now is just work, unless anyone has general questions about factoring or like math that you would feel there would be a benefit talking as a class rather than as individuals. Otherwise, let's just work, and I'll walk around and try to help people. And if you're strong at programming, please help your peers. This peer mentorship is like among the best ways to actually learn. This is provable. So otherwise, and then chats, if you need us, I'll just yell, like turn on your audio and say something, and I'll come to the screen. Okay, so get to it.
Yeah.